Alright, chapter 19 is our last chapter for the year, so we are going to model this chapter after how we do things in AP Chemistry. So you have to take on a little bit more responsibility. It's the end of the year, you're almost moving up to the next grade or graduating if you're a senior, so it's time for you to take life into your own hands and get this done. So make sure you check out the checklist to know what you're supposed to be doing each day, when things are due, and every day in class there'll be time for questions. So if you don't get something when you watch the video, then ask in class. Okay? Chapter 19 is all about acids and bases and how they have two different faces. So check out the awesome, I think anyway, video on It's Learning. It's a song called Acids and Bases Have Two Different Faces. Has some good stuff in there. If anything, it's pretty catchy. And we're going to talk about the differences between the acids and bases, why they have two different faces, and the strengths of them. So acids versus bases. Acids are very sour tasting, whereas bases are usually bitter tasting. And the bases are really slippery when you have them on your fingers, kind of thing. So over the years, chemists had known properties of acids and bases, but it wasn't until 1887 when Svante Arrhenius proposed a new way of defining and thinking about acids and bases, where he said it's based on the electrolytes, where acids produce hydrogen ions in aqueous solution and bases produce hydroxide ions. This theory works for strong acids and bases because strong bases already have a hydroxide, so it's already there to help us out. So just thinking back from chapter 9 when we did our naming and formula writing, we said that an acid, it has the name acid in it, or had the word acid in the name, begins with a hydrogen ion as the cation. So like all those listed, hydrochloric acid is HCl, nitric is HNO3. They all start with an H with a +1 charge. And we would write them as if we were writing an ionic compound. So with acid dissociation, this is saying that when you have an acid dissolving in water, then it breaks up into its hydrogen ion, and which we're going to call a proton here, and then its anion. In this case, for hydrochloric acid, it is Cl. The newly released hydrogen ions will join with the water molecules to form what are called hydronium ions. So the hydrochloric acid is our acid, and then the base in this case is water. Notice the ball and stick figure models. And then we have H3O with a +1 charge, and that's our hydronium. And then what's left over is the chloride ion. So this is just showing you how the hydronium can be formed. With bases from Arrhenius, he said everything had to have a hydroxide to make it a base. So sodium hydroxide, potassium hydroxide, these are all very common. You can pause if you need more time to write down the common names. But they all have OH in them. They all have the hydroxide. And so that was kind of what he thought they needed to have. So one more time, because it has a hydroxide, you can see that when it dissolves, it'll break up and form that hydroxide. There were some problems though, because Arrhenius's definitions were not very broad, and they excluded some substances that have been acidic, that can have acidic or basic properties. So for example, both I have pictured here, sodium carbonate and ammonia both act as bases when they are in aqueous solution, but neither of them has a hydroxide in it. So we had to have a new model, and this was suggested by Brodsett and Lowry, where an acid is a proton donor and a base is a proton acceptor, where here proton is signified by the H +1. Okay? So based on this theory, the new theory, then this is showing how ammonia can behave like a base, where ammonia is NH3, right? And when it reacts with water, what happens is the water will give one of its H's, one of its protons, to the ammonia to make NH4, ammonium, +1, and then what's left over is hydroxide. And since the hydroxide is left over, it's present, that's how it can be a base. So when we have this whole adding to water, or really anything, we have what are called conjugate acids and conjugate bases, okay? Where if we have our regular acid with a base, the acid is the one that's giving up the H+, and the base is the one that's getting the H+. So on the product side, whatever the base was, plus an additional H, plus an additional charge, that's what makes the conjugate acid. Okay? And then the acid, when it loses the H and it loses a charge, whatever is left over is the conjugate base. So just one more time to reiterate, H3O plus 1 is called hydronium. Water is polar, so it attracts the proton in this situation. The conjugate base is everything left over after the one proton is lost. So we get what's called a conjugate acid-base pair, which consists of two substances related to each other by the donating and accepting of a single proton. So where are the pairs? Well, here in this equation, this is going to be our acid. Okay, sorry, it's ugly. And this is going to be the base. So the acid is giving up an H and a +1. So what's left over after the acid has given it up is going to be the conjugate base. So this has, the chloride has lost an H and it's lost one charge. And so that's going to be the conjugate base now, what's left over. And so the acid is related to the conjugate base. Okay? Then the product that gains an H, or has one additional H and one additional charge, is going to be the conjugate acid because it has more protons. And so the base is connected to the conjugate acid because the base is what gained the additional H and it gained the additional charge. Okay, so the acid always goes with the conjugate base, and then the base always goes with conjugate acid. They're like opposites working there. Okay? So for example 1, we want to know if they represent a conjugate acid-base pair. Okay? So we just have to see if the only difference between them is an H and a +1 charge. And if so, then yeah, they are. And if not, nope, they're not. So for the first one, we have HF and F with a -1 charge. Well, the only difference between the two is the second part does not have an H, and it lost one charge because it started with neutral and now it's negative. So yes, that is a conjugate acid-base pair. Next, we have NH4 + 1 and NH3. So the only difference there, they have a difference of 1 H. And the first one, ammonium, it has a +1 charge, and then ammonia is neutral. So yes, that is a conjugate acid-base pair. And the last one, HCl and H2O. Well, there's a difference of 1 H, but there's no difference in charge, and there's no Cl in the water. They're not the same things. So that is not a conjugate acid-base pair. That didn't make a very good X, did it? Okay, so it has to be related with everything even after the H's are matched up in order for it to be a conjugate acid-base pair. And our last example, we want to write the conjugate base for each of the following. Okay, so to write the conjugate base, we have to lose an H and a +1 charge. Okay, so based on what we have, the first one we have is HClO4. So we need to take off an H. Well, there's only one H to start with, so that means I'm just taking off the H. I'm left with the ClO4. And then it had a neutral charge, so we have to lose a charge. So if it started off at neutral and we're losing it, that means it becomes a -1 for its charge. Okay, so that would be the conjugate base. We lost an H, we lost a charge. Okay, next we have H3PO4. This time we have multiple H's, so we're just going to take one off. So we're going to be left with H2PO4. Okay, and then it started it out as neutral, so that means it's going to have a -1 charge now. Okay, and then last but not least, we have CH3 and H3+. That's a lot of H's. We're losing an H, right? Let's take the H off of the end. So we're going to keep it CH3, and then it's going to be NH2. So that's where we take our H off of. Okay, and then it started out with a +1 charge, but we have to drop it down 1, so now it's going to be neutral. So NH2 at the end is our final answer. Okay, this is the end of our notes. One thing, if you need to write a conjugate acid, then you would have to gain the H+1. Okay, so because you're going to have to do this in the acid and the base paper. So let's say that we had NH3, okay, and we wanted to gain an acid or become the conjugate acid. We have to increase the number of H's, so it's going to turn into NH4. And then we also have to gain a charge, or like make it more positive, right? So it's going to be NH4 with a +1 charge now. So conjugate acid is the opposite way of what we did in example 2 in order to make it. Okay? You'll be able to ask questions in class over this material, but you need to do numbers 1 through 6 on the acids and bases assignment now.